Physicists have long been fascinated by black holes, a phenomenon that has intrigued scientists for over a century. These enormous entities that defy our understanding of gravity remain largely invisible to us. A black hole, with a mass that could be anywhere from 2 to 4 million times that of the Sun, is incredibly powerful. Yet, due to research conducted over the past few decades, we've transitioned from knowing virtually nothing about them to uncovering more and more, sometimes in surprising ways. Just recently, a breakthrough has occurred. Researchers, including those at the Kaku Institute, reported that they had successfully peered inside a black hole. This new data has illuminated facets of the universe that science may have overlooked in the past. Let's dive into black holes and discover what lies within. Space is vast and awe-inspiring, but before getting into the details of what was shown in recent findings, it's crucial to grasp the basics of what black holes are. Many people are familiar with the idea of black holes, yet there are still significant gaps in our understanding of them. The concept of a black hole became theoretically possible in 1916 when the general theory of relativity was published by Albert Einstein. However, the idea of black holes remained purely speculative until the 1960s, when scientists first observed compelling evidence supporting their existence. While studying the binary star system Cygnus X1, astronomers discovered an unusually bright blue star emitting X-rays. This star wasn't a normal celestial body, it was orbiting around a mysterious, massive object. After further examination, it became abundantly clear that the X-rays were not simply floating around in space but were being pulled toward the dark entity, confirming the existence of black holes. This was a groundbreaking discovery, demonstrating that black holes were not just theoretical constructs but real phenomena. The significance of this discovery can't be overstated. It meant that an entirely new class of objects existed in space, requiring urgent and thorough study. Researchers from around the world turned their attention to black holes with renewed focus. The first identified black hole, Cygnus X1, is located about 6,000 light-years away in the Cygnus constellation. On Earth, it appears many times brighter than our Sun and possesses an immense gravitational pull, so powerful that not even light can escape it. This is why it's termed a black hole. The concept of a black hole is both fascinating and intimidating. It refers to a region in space where the gravitational force is so intense that nothing, not even light, can escape its pull. Anything that gets too close to a black hole is inexorably drawn in, doomed to be lost forever. This danger makes the study of black holes not just intriguing but essential. However, are we in any immediate danger from them? Despite the closest black hole being about 500 light-years away, this distance still raises questions about potential risks. However, the full extent of black holes remains unknown. After the discovery of Cygnus X1, astronomers began searching for others. It is now believed that there may be as many as 100 million black holes in our Milky Way galaxy alone, though detecting them remains a formidable challenge. Estimates suggest that millions of them exist within our galaxy, underscoring the importance of studying these enigmatic objects. The primary concern with black holes is their immense gravitational pull. This pull is so strong that it drags everything, even light, into itself. The core of the black hole, known as the singularity, is where all the matter that falls into it is compacted into an infinitely dense point. In simpler terms, black holes act as cosmic vacuum cleaners, sucking in everything in their vicinity. If someone were to fall into a black hole, they would be gradually stretched and compressed until they were reduced to a singularity. This process is incredibly slow, meaning the individual would meet their end long before the final, irreversible stage. Yet, despite the apparent danger, black holes are so widespread that they cannot be ignored. Even though the closest one is far away, the sheer quantity of them in our galaxy makes them a significant subject of scientific investigation. In 2019, scientists achieved a historic milestone by capturing the first-ever clear image of a black hole, the supermassive black hole at the center of the M87 galaxy. This photograph was obtained over several nights, and with each exposure, new insights were gleaned. The data was then painstakingly pieced together to reveal a clearer picture. The most striking discovery was that a black hole isn't just a single void in space, it consists of 3 distinct layers. The first layer is the event horizon, which marks the point beyond which nothing can return. Once an object crosses this line, it is inevitably drawn toward the black hole. The second layer is known as the photon sphere, where light is trapped in orbit. Any light that enters this region is caught in the black hole's gravitational grip and cannot escape. Finally, the third layer is the singularity, where matter is crushed down to a single point in spacetime, creating an environment where the laws of physics as we know them cease to function. This breakdown of the laws of physics is one of the many reasons studying black holes is so fascinating and challenging. What's even more intriguing is that each black hole behaves differently. While they tend to share the same fundamental layout, the way each one functions can vary. Unlike most objects in the universe that we can study directly, black holes can only be examined indirectly. Researchers use observations of the radiation emitted by black holes and the gas and dust surrounding them. It's impossible to send a probe into a black hole because anything that crosses the event horizon is pulled into the singularity, where it would be crushed to an infinitesimally small point. This presents a significant limitation for scientists. Without the ability to study black holes in the traditional way, researchers are forced to work with two-dimensional models to understand these three-dimensional objects. Furthermore, black holes come in different shapes and sizes, making them even more challenging to study. Scientists have developed several theories to explain how they form, with one of the most prominent being the idea that black holes originate from collapsing stars. When a star runs out of fuel, it can no longer generate the energy needed to counteract the force of gravity, causing it to implode. When a massive star reaches the end of its life cycle, it undergoes a dramatic transformation. As nuclear fusion ceases, the outward pressure that once balanced gravity collapses inward. If the remaining core is dense enough, typically more than 3 times the mass of the Sun, the star's collapse is unstoppable, forming a black hole. This process is known as a supernova, a massive explosion that briefly outshines entire galaxies before leaving behind either a neutron star or a black hole. However, not all black holes form from dying stars. Scientists have identified different types of black holes, each with unique origins and characteristics. Types of black holes. 1. Stellar mass black holes. These are the most common type, forming when a star between 3 and 20 times the Sun's mass collapses. They range from a few to dozens of solar masses and are scattered throughout the galaxy. 2. Supermassive black holes. Found at the centers of galaxies, these cosmic giants possess millions to billions of solar masses. Their formation is still a mystery, but they may grow over time by merging with other black holes and consuming vast amounts of matter. The supermassive black hole at the heart of the Milky Way, Sagittarius A*, has a mass roughly 4 million times that of the Sun. 3. Intermediate mass black holes. These range from hundreds to thousands of solar masses, filling the gap between stellar mass and supermassive black holes. Though theorized for decades, only recently have astronomers gathered compelling evidence of their existence. 4. Primordial black holes. Unlike other black holes, these are thought to have formed shortly after the Big Bang. If they exist, they could provide insights into the early universe and even dark matter, one of the biggest mysteries in physics. How do we detect black holes? Since black holes do not emit light, scientists rely on indirect observations to detect them. The most effective methods include gravitational lensing. Black holes bend and distort light from distant stars, creating a magnifying effect. This allows astronomers to infer the presence of an unseen black hole. X-ray emissions. As matter falls into a black hole, it heats up to millions of degrees, emitting powerful X-rays that telescopes like NASA's Chandra X-ray Observatory can detect. Gravitational waves. When black holes merge, they release ripples in spacetime. The Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo detect these waves, providing direct evidence of black hole collisions. The future of black hole research. Recent advancements have revolutionized our understanding of black holes, but many mysteries remain. Scientists continue to develop new ways to study them, including the Event Horizon Telescope, EHT, a global network of radio telescopes working together to capture detailed images of black holes. The first ever image of a black hole, released in 2019, was just the beginning. Simulations and AI modeling. Supercomputers are being used to simulate black hole behavior, helping scientists predict their interactions with galaxies and other celestial bodies. Hawking radiation. Proposed by physicist Stephen Hawking, this theory suggests black holes slowly lose mass over time due to quantum effects. If proven, it could redefine our understanding of black hole lifespans and even provide insights into quantum gravity. Could black holes be portals? One of the most intriguing questions is whether black holes could serve as wormholes, shortcuts through spacetime. While general relativity allows for the possibility, current physics suggests that any matter passing through a black hole would be destroyed. However, some theories, including those in quantum mechanics, propose that black holes could be gateways to other universes. Final thoughts. Black holes remain one of the greatest enigmas of modern science. While we've come a long way in understanding their nature, there is still much to learn. As technology advances, we may one day unlock their deepest secrets, revealing more about the very fabric of the universe. The journey to understanding black holes is far from over, perhaps the biggest discoveries are yet to come. If a star is massive enough, its collapse continues until it becomes a singularity. NASA researchers have focused on a particularly powerful galaxy, M87, where they observed a vast whirlpool of hydrogen gas rotating at an astounding speed of 1.2 million miles per hour. Despite the immense forces at play, the gas didn't fly apart, leading scientists to conclude that there must be a massive object at the center of the galaxy holding it all together. This object turned out to be a black hole, weighing billions of times the mass of the Sun. In 1963, Roy Kerr, a New Zealand mathematician, used Einstein's equations to provide a model for rotating black holes. Kerr's theory suggested that instead of collapsing into a singular point, a rotating black hole could form a ring of fire or an accretion disk. This disk would rotate so rapidly that the outward forces would counteract the gravitational collapse. Kerr's work also introduced the concept of the Einstein-Rosen bridge, or wormhole, a hypothetical tunnel that connects two distant points in spacetime, potentially even linking parallel universes. The concept of wormholes has fascinated scientists for decades. If black holes are indeed connected to wormholes, they could offer a shortcut through spacetime, allowing travel between distant regions of the universe or even different times. However, even if wormholes do exist, it's unlikely that we would be able to travel through them anytime soon. According to Einstein's theory of special relativity, the speed of light is the ultimate limit for how fast anything can travel, presenting a barrier to using wormholes for faster-than-light travel. Nevertheless, wormholes continue to be a fascinating theoretical subject. If they could be stabilized, they might provide a means of traveling across vast distances of space or even to different times. Some physicists also suggest that wormholes could offer a mechanism for time travel. The challenges of crossing a wormhole, however, are immense. They would likely be unstable and surrounded by extreme radiation and gravitational forces. To truly understand the nature of black holes, physicists will need to develop a single theory that combines both Einstein's general relativity and quantum mechanics. One promising candidate for this theory is superstring theory, which proposes that nature's fundamental particles are actually tiny, vibrating strings. These strings could explain many of the mysterious phenomena observed in the universe, including the formation of black holes and wormholes. Superstring theory also suggests that black holes, wormholes, and other exotic solutions to Einstein's equations may arise due to the bending of spacetime by these tiny strings. Despite its promise, superstring theory requires the existence of additional dimensions of spacetime that are too small for us to detect. However, research into black holes and their mysteries continues to push the boundaries of our understanding. One of the most groundbreaking ideas related to black holes is the concept of Hawking radiation, proposed by physicist Stephen Hawking in 1974. This theory suggests that black holes are not completely black but emit faint radiation due to quantum effects near their event horizons. This radiation could cause a black hole to slowly lose mass over time, eventually leading to its evaporation. Hawking radiation is difficult to detect due to its weak nature, but it offers valuable insight into the behavior of black holes and their role in the universe. Black holes also provide a unique laboratory for studying the interaction between gravity and quantum mechanics. The extreme conditions near a black hole's singularity are where both quantum mechanics and gravitational effects come into play, making them a key area of research for physicists working on a quantum gravity theory. The study of black holes may also hold clues to understanding the origins of the universe. Some theories suggest that the conditions near a black hole could offer insights into the birth of spacetime itself. If wormholes do exist, they could provide a mechanism for exploring vast regions of spacetime, offering new possibilities for interstellar travel. Although these ideas remain speculative, they continue to inspire researchers to explore the deepest questions about the nature of our universe. The role of black holes in cosmic evolution. Black holes are not just destructive entities, they play a crucial role in the evolution of galaxies. Supermassive black holes are found at the centers of most galaxies, including our own Milky Way. These massive objects influence their surroundings, shaping the structure and behavior of the galaxies they inhabit. One of the key mechanisms through which black holes affect galactic evolution is feedback. As matter falls into a black hole, it heats up and emits powerful jets of energy. These high-energy outflows can regulate star formation by either triggering new star births or suppressing them by dispersing gas clouds needed for star formation. This process helps explain why some galaxies stop forming stars and transition into quiescent elliptical galaxies over time. Recent observations from telescopes like the Event Horizon Telescope, EHT, and the James Webb Space Telescope, JWST, are providing unprecedented insights into the nature of black holes. In 2019, the EHT captured the first-ever image of a black hole's event horizon in the galaxy M87, confirming many predictions of Einstein's general relativity. These breakthroughs are bringing us closer to understanding the true nature of black holes. Could black holes be gateways to other universes? Some physicists speculate that black holes might be more than just cosmic vacuums, they could be gateways to other universes. This idea is rooted in theories like the multiverse hypothesis, which suggests that our universe is just one of many. According to this idea, if an object were to cross a black hole's event horizon, instead of being destroyed, it might emerge in an entirely different universe. Some interpretations of loop quantum gravity suggest that a black hole's singularity could be replaced by a quantum bridge, preventing complete collapse and allowing matter to pass through. While this remains purely theoretical, it opens the door to new ways of thinking about black holes and their place in the cosmos. The search for primordial black holes. Another intriguing possibility is the existence of primordial black holes, which may have formed in the early universe, shortly after the Big Bang. Unlike stellar black holes, which form from collapsing stars, primordial black holes could range from microscopic sizes to several times the mass of the Sun. Some scientists even propose that these tiny black holes could explain dark matter, the mysterious substance that makes up most of the universe's mass but has yet to be directly detected. If primordial black holes do exist, they could provide insights into the conditions of the early universe and the nature of dark matter. Researchers are currently searching for signs of these elusive objects using gravitational wave detectors like LIGO and Virgo, as well as studying their potential effects on cosmic structures. The future of black hole research. The study of black holes is entering a new era. Future space missions, such as LISA, Laser Interferometer Space Antenna, aim to detect gravitational waves from merging black holes, offering new insights into their behavior. Meanwhile, advancements in quantum physics and artificial intelligence may help decode the complexities of these enigmatic objects. Ultimately, black holes may hold the answers to some of the deepest questions about the universe. What happens at the center of a black hole? Can black holes be used for interstellar travel? Do they connect to other dimensions? Could they reveal a unified theory of physics? As technology advances and our understanding deepens, black holes will continue to be one of the most exciting frontiers in astrophysics, offering glimpses into the fundamental nature of reality itself.